but I don't know. Okay.
Okay, so next up we have Dhruv. Dhruv will be talking about verification of DNS.
Yeah, so the topic of my talk is reachability analysis of the domain name system. My name is Dhruv, and I'm the information security group at ETH Zurich under the supervision of David Basin. We don't really see this name very often, where you kind of merge reachability analysis and domain name system together. So today we'll be looking into what the problem really means, and hopefully you won't be needing coffee by until the end of the talk. So the structure of the talk, in this talk, I'll be first giving you a slight overview of DNS because, in this talk, I'll be giving you a slight overview of DNS because I realize that many people don't really know the nitty-gritty details. Next, I'll be talking about the problem, then the state of the art, and finally, the results, and then I'll conclude. Okay, so what is DNS? And we start with a gig. So let's say you're at a party and you're getting drunk, and at some point you really want to go home, so you call a cab. And you tell the cab driver you just want to go home. You don't tell him where the home is. So the scene one is the cab driver is a creep. He already knows where you live, and he just says, well, come on in, I can take you home. The more normal scenario is the cab driver gets confused and just asks, okay, where is your house? I don't know. And at this point, if you really want to go home, you will tell him the real address, which would typically comprise of a street number, a city name, a country code, postal code, or something a bit more concrete than just home. And this is pretty much what happens within computers as well in the internet when there is an Alice who wants to, let's say, visit a certain domain. What she does is she asks her browser that she wants to go to inter.net, for example. And the browser then forwards this query to something called a resolver, which is typically your internet service provider. And if the service provider already knows the answer, which is the IP address of the computer that you want to reach, or the server that you want to reach, okay, sorry. Now that should not be dropping. Okay, so if the resolver does not know the IP address, it then forwards this query to a name server, which is lying somewhere out there in the internet. And the name server also has an IP address of its own. The query typically contains two portions. One is a domain name, which is basically the query that was the domain name that was initially queried, and a type, in this case, that's A, which is asking for the IP address of inter.net. The name server then checks its local information and gives back a response, which is typically a bunch of resource records. And a resource record basically is a tuple which contains 4 parts. The first part is, again, a domain name. The second part is the type of the resource record. In this case, it matches the query type, but it may not always do so. The next part is something called the time to live, which kind of tells the resolver how long he or she can reuse the same record, like this piece of data. And finally, you have a value. In this case, the value is an IP address because the type was an A type. And there are a couple other types. We won't be going into a lot of types, just going to cruise. Okay, but in the network, we don't have one name server. We have multiple name servers. And typically, the name servers are arranged in a hierarchical pattern, where the top name server is called the root. And below them, we have various domains and subdomains, and that's a tree-like structure. And once again, we have Alice, who's asking her resolver to go to inter.net. And resolver typically, there might be a question, which is, how do you know whom to ask first? And this is where the resolver is usually hard-coded by at least one name server in the network, and that name server is usually the root of the network. So the resolver then forwards this query to the root name server. The root name server's response, well, okay, I don't know where inter.net is, but I do know someone whose name kind of matches the query that you just sent, which is a .NET name server. Why don't you ask him? And to do that, it gives back a response which contains 2 records. The first one is a delegation, which is the red arrow, and the NS record. It says that going forward, every time you see a .NET query, just go and ask .NET, don't ask me. And .NET lives in the IP address IP3. Okay, so the resolver then forwards this query to IP address 3. Once again, the .NET name server says, well, I don't know where your query is, but I do know someone whose name matches even more with your query. Why don't you ask him? And the resolver goes forward and asks the same query to ns.inter.net, which is at IP address 4. And at this point, the guy says, OK, I do know where you want to go, and this is the IP address. Have fun. But some things can go wrong. So what if, after all of this, the final name server ns.inter.net is actually malicious? And instead of giving back an IP address, it says, well, I don't know where inter.net is, but I do know someone else whom you can ask. However, and not just one person, I know like multiple people whom you can ask. However, at that point, he does not give the IP addresses of these people. So now the resolver is stuck figuring out where to ask next. It knows the names of these servers, but it doesn't know where they live. So it must first resolve, and that's DNS protocol, these name servers' names first. And to do that, it again goes back to the root. The root now says, well, you need to go to the .com name server. And at that point, when it asks the .com name server, .com clearly knows that ns1.inter.com is nowhere in the internet. So it just says, I don't know, and doesn't exist. So the resolver says, OK, fine, no problem. Why don't you give me the IP address of the next guy I received? Well, again, I don't know. And finally, why don't you give me another one? And at this point, the name server is clearly confused, and it's just its traffic flow is just bogged down by these bogus queries that are being asked by the resolver. Both are busy. And this is something called the NXNS attack, which was revealed in 2020, and it's mildly severe, and that were found in all the resolver implementations out there. So this is how things can go wrong, and this is something that we would like to catch before things are deployed. Okay. So this attack kind of belongs to a class of attacks called DOS attacks, which stands for denial of service. And that's because the name server can't actually respond to real queries and is getting stuck doing boring stuff. And it can be seen that in 2022, DNS was 20% responsible for the class of all DOS attacks, and recently increased by a lot. And in 2024, it was actually responsible for more than 50% of the DOS attacks on the internet. So clearly, we need to do a security analysis. And because the scale of this whole thing is huge, we want to do it in an automatic way. So that's it with the motivation. And now let's do some math. So we have the network. What does the network really know? So network is basically just a bunch of name servers which have IP addresses. And each IP address or server stores some local information, which are just bunches of records. So you can actually represent it as a function which just takes IP addresses to bunches of records. Okay, and we call this a zone file configuration, this function. And typically, a zone file configuration uniquely determines the behavior of DNS because that's just all the knowledge the network has. Okay? So what is the problem? The problem that we are interested in is asking that given a zone file configuration, which is this function, is it possible to have a DNS attack, and this attack being specified by a trace property phi? And typically, we actually represent the trace property phi by an automaton that represents the trace property, the class of languages, the class of traces which are bad. And if there's an attack, you would also like to report the attack. Okay. So there has been a lot of work since long, long back. And until 2020, the main way of working on this was testing. And I'll be comparing a few more works across three main metrics. The first one is soundness, which basically means that if I report an attack, it is an actual attack. The second one is completeness, which means that you're actually exhausting the set of all possible behaviors. So if in the absence of attacks, you're also reporting that. And finally, we have robustness, which means that if ever the DNS standard changes, how easy is it for you to change your internal model to kind of keep yourself up to date? So in testing, we have soundness because you're basically just simulating the real world model. We don't have completeness inherently. And we have robustness because once again, you're just simulating the real world model. So since 2020, there have been two works, particularly groot and DNS mod. DNS mod is basically a mod wrapper, like a symbolic fuzzing wrapper around groot. And both of these have tried to give a formal treatment to DOS analysis. However, groot lacks soundness, completeness, and robustness. At the time of publication, groot was actually considering a very limited model of DNS, and it was sound with respect to that, but it was still not complete, and it was still not robust. DNS mod, on the other hand, is robust because at the base, it's just using rewrite rules to kind of change the semantics of DNS, but it also lacks soundness and completeness. So what's the goal here? Clearly, testing cannot ever get completeness. So what we would like to do is at least get soundness, completeness, and robustness using formal treatments. And this is also what are the contributions of this work. Okay, so how do we do it? Let's consider the model. The name servers that we talked about are fairly simple. They basically just get a query and give a response, and they just look at the local databases. They never gain any knowledge, lose any knowledge, so it's stateless. Resolvers, on the other hand, are complicated characters. They keep three main components in their state. The first thing that is keep is a priority list of name server domains to query. Now, it's important to note that they store domains and not IP addresses. So they store the names of people they can ask. Next, they store a cache of records. Oh, sorry, that's a mistake. They store a cache of records, and each record has its own lifetime, which is the time to live that we just saw. After that, the resolver cannot use these records again, and these are received from responses. Finally, we have a stack of pending queries, and this can occur in the attack that we just saw. For instance, if you're asking, if you want to go to sigplan.org, and there is no IP address that you received, and instead you get a delegation to ns.sigplan.org, you will now be pushing this onto your stack and querying that first, stowing away your initial query. So now what's a poor man's approach for this thing? You have these three components, and for the first thing, you will store it as an ordered set of domain names. For the cache of records, you can just have a bunch of timers, with each timer identified by a record element. And once the timer is out, you cannot use a record anymore. And you have a stack of pending queries, which can just be represented by a stack of queries. OK, so this means that you finally have a message passing system where name servers are just finite state systems, and resolvers are pushdown systems with timers. Now, while this may seem easy, there is a catch. And the catch is that all of these things, all these components that we just saw, have domain names stored within them. And the number of domain names we have are huge. And sometimes you even need to store sets of domain names, and that makes your configuration space exceed the number of atoms in the universe, just to put matters in perspective. OK, so as good formal methods people, what we do is we abstract. And in this paper, what we define this as is a syntactic domain congruence, which depends only on the zone file configuration and not on the behavior of DNS, so to speak. So we represent DNS by a free monoid over the set of all strings using an underlying alphabet. It's not important what the alphabet is. And what we do is we abstract it and we bring it down to a finite monoid. And this is typical in algebraic language theory. The way we construct this homomorphism is by parsing the zone file configuration, the records in them, and carefully constructing some regular languages, and then using their syntactic congruences, which is very close to Myhill-Nerode congruence, as building blocks for the finite monoid. And what we have in the end is that if two domain names are mapped to the same element in the finite monoid, they are coined to be equivalent. And we have some couple of cool properties, whatever these may mean, and we don't have enough time to actually go into that. But essentially, it conveys that if D and D prime are equivalent, they're semantically identical for DNS. That means DNS cannot distinguish between these two domain names. So once we have this function with this homomorphism, we again take the inputs that we have. We lift these inputs in the abstract world to the abstract world, and we have zone file configurations and automata with finite monoids as the domain names. We then use the poor man's construction once again, but this time we have finitely many domain names. And this finiteness is actually much smaller than the initial finiteness we were talking about. And what's more is that any trace in the abstract model is having an equivalent trace in the concrete world. So you can actually map back. And this is proved using a generalized notion of bisimulation that we also proved in the paper. But note that at this point we have a message passing system where potentially it's possible for multiple components to cyclically talk to each other. And this is something which is Turing complete. And hence, if you're talking about reachability analysis of such systems, it becomes undecidable. So this is where we made another observation where we showed that DNS is in fact eager, which means that in certain portions where actually packets are transmitting, as soon as I send a packet, everything else stops, and the person is literally waiting for my message to be received, and I'm also waiting to receive a response. Until then, I'm not going to do anything. And this is something called as eagerness, which was introduced in 2010 by Heusner et al. And using this, it actually becomes possible to reduce this model to a simple pushdown system, which is trace equivalent. That means any trace here is actually also a trace in the previous model. And now we have a finite automaton. We have a pushdown system. And what we do is we just ask the language emptiness problem for this model. And if the language is non-empty, you can actually get a trace. And if it's not, that means the situation is safe. If it's empty, then the situation is safe. OK. However, the complexity of this algorithm is pretty bad. It's doubly exponential in the size of the zone file configuration, which means that if you have a huge zone file configuration with, like, I don't know, 100,000 records, then yeah, it'll take time. Okay, so with that, I would like to summarize that we have come up with a sound abstraction, which is facilitating a decision procedure for DNS verification. Then it adheres to a generalized notion of bisimulation, which allows concrete witness generation. And at the time of submission, we didn't have an implementation, and the reviewers gave us a lot of heat for this, but we now do have an implementation, and it's currently an ongoing work in progress. For future work, we would like to extend this setting to multiple ISPs, because that's what's happening in the network. However, it's not really needed for actually recovering most of the common attacks. And we would also like to dynamically update this distributed database, because that's also something that happens on the internet often, like when you want to update something in the local databases of name servers. So with that, I will be opening the stage for questions.
Thanks. Perhaps two short questions. One, does it make sense to consider any temporal properties besides plain reachability? And the second, any lower bounds, proved lower bounds?
Okay. So about temporal properties, there's something which could be a resource consumption feature. And this is related to some of the attacks. However, at the end of the day, the temporal properties would just boil down to symbolic properties, and they can again be represented by some sort of finite state machine, which kind of follows through the typical emptiness of timed automata. So okay, there is something for liveness which is called availability. The thing is, this is kind of like a one-shot verification. So once you check your zone file configuration, you don't need to check it again. You just deploy it on the internet, and everything works. So availability kind of makes sure that all the servers in the network are reachable. And that's something that is equivalent to liveness when we talk about in the world of the internet, let's say. However, sometimes if there are dynamic updates, then liveness becomes a thing, because with an update, now suddenly something may become unavailable. And yeah, these will be questions that we can ask there. And yeah, that's something that I'm also thinking about, but I don't really have an answer to yet. And about lower bounds, there was a paper which actually showed that DNS is at least as powerful as a pushdown system, which kind of is something that we already showed. But well, it's just kind of like saying that you have a resolver in the network or not. And that makes the complexity at least cubic. But there's nothing better that is known yet, and it's something that we have also not looked into. We just looked into an upper bound.
Questions? Okay, so then let's thank